Swayam Prabha. Digital India. Educated India.
In the earlier module, we have looked at primary energy analysis, where we looked at different options from the point of view of how much primary energy they are using. We now extend this and move forward to look at a new technique, the life cycle analysis. And within life cycle analysis, we are going to focus on net energy analysis. So we will look at some applications of these techniques, different criteria, and how this can be used to help in decision making. We've seen earlier the decision making based on an economic analysis, and at sometimes it is we want to look at the different options from the point of view of how much energy it takes over its life cycle. So the whole field of life cycle analysis, or LCA as it is known, started in the early 1960s, 1970s. In the initial phase, there were multiple methodologies, and in the 1990s, there were two different societies, the CETAC and the ISO, which tried to standardize and provide a set of methodologies for carrying out life cycle analysis. So let us look at what is life cycle analysis. You may want to look at the international standard ISO 4040, which sets out the methodology for life cycle analysis, and you can look at this. It is available in the public domain. There are some additional values. This one is the 1997 edition, and this provides a framework for carrying out environmental management or life cycle assessment, and the principles and the framework. This initially LCA was used to compare different products, and mostly products for packaging. So we looked at the entire life cycle from the point at which it was manufactured, right from raw materials to the use and to the disposal. So all of this constitutes the life cycle analysis. So in life cycle analysis, the basic steps involved are: first, we compile an inventory of relevant inputs and outputs, the different inputs which are coming into the process and the outputs for the process. And then for each of these, we evaluate the potential environmental impacts associated with these inputs and outputs, and then we interpret the results. Now there are two approaches here. We can do what is known as cradle to gate or cradle to grave. And this typically means that we start with the initiation, the actual manufacture, and then to the gate where it is the produce and used. Cradle to grave means we also look at the disposal phase. So the full cycle, if we want to take, it will be a cradle to grave analysis. In some cases, we just do the analysis till we get the end use, and that's the cradle to grave. So if we look at the methodology for life cycle analysis, the first step in the life cycle analysis is to identify the goal and the scope, define the scope and the goal. Once we define the goal and the scope, we can then look at what is the inventory, what are the inputs and outputs going into the system boundary that we have, and of course there is some iteration both ways between the goal and the inventory analysis. Based on this, we can then do an assessment of the different impacts. Again, and then in all of this we would interpret the results. So, there is scope for interpretation. We have these values which will be there, and there will be multiple different criteria, and then this will also. So, this essentially represents the framework for LCA. Now, what you need to do is you need to take some examples so that you know how to do this kind of calculation, and it will be useful in a whole variety of examples. And we will take some examples from literature. This entire framework will then go for this will give us the direct applications, and there are different types of applications. We can look at it for improving the current mechanism so that we can reduce the environmental impact. The second is we can look at it for decisions for product development, we can look at it for choices, we can look at it for strategies for companies, we can look at it for policy analysis. So, what we have just seen, this is, let me just put the pointer, this is what we have just now seen. This was the LCA framework, this is from the ISO manual, and this gives you finally the direct applications that we are talking of. So, as we move forward, when we look at the product system, we may want to decide in the system the different kinds of flows which are there in the system. So, when we are creating a product, we may actually build in some materials which will come in, raw materials, and then there will be flows into that system. These raw materials will be converted, and there is a production phase, there is a use phase, there is a recycling and a reuse, and then the waste and the waste treatment, there is some energy supply and transport, and finally there is this product flow which we are talking of. So, this could be an example of a product system based on which we can do the life cycle analysis. When we talk about the goal, it is important for us to understand what is going to be the application of the LCA, and depending on the application you may modify the methodology, decide the system boundaries. So, what is the intended application, what is the reason for the study, who is the audience, who are the people who are going to use this LCA, maybe it is being used for some comparative assessment. So, this goal, and then based on the goal identify the scope, what is the product system, what is the functions, what kind of, we may want to define a functional unit. This is very important in most of the LCA that we carry out, that we define clearly a functional unit, use it as a basis for comparing between different things, identify the system boundary. Also in many of these cases allocation procedures, because in your process we may have multiple products, and to allocate the energy flows or the material flows to one of the products, we will have to have a basis by which we make this allocation. There are a large number of different life cycle analysis which have been done, which are available in the public domain, in the papers and in reports and in books, and depending on your application you can always find something which is similar which has been done, but then you may want to do that for your own local context, because globally or nationally or locally, there are differences in the way, in the electricity mix, in the kind of procurement of raw materials, in the environmental impacts, and so the an LCA which has been done for Europe may throw up different results from the LCA which has been done for an Indian context. So, as I told you, with the functional unit is a very important point in your starting point for the LCA. We must define a functional unit which is related to the purpose of the process or system. So, and it should be consistent across the options being assessed. So, for instance, if we are looking at a power plant, we may say we want to generate 1 megawatt hour of electricity. Per megawatt hour of electricity, how much is the energy input, how much are the emissions, and then we can compare coal based plants with photovoltaic based plants or wind based plants or biomass based gasification. And then the quantified performance of a product system, which is for use as a definition of a functional unit, is the quantified performance of a product system for use as a reference unit. So, initially once we start the study and we identify what is the use, we can then define a functional unit, then compare all the options based on that functional unit. So, let us take one of the interesting studies which is there in literature. There are a number of papers on it, is when we look at when you have tea or coffee, there are many different options by which you can have your tea coffee in. So, you can look at a paper cup, you can look at a cup which is a polystyrene cup which is basically plastic, and one can also think in terms of a ceramic cup which can be washed and reused. One can think in terms of a glass cup which is made of glass, again can be washed and reused, and you can also think in terms of in rural India and even in some of our towns, we still have those coolers which are fired clay, and you can have tea in that, and it's a disposable cup, but the broken cups are again fired and reused. So, one can think in terms of how do these, when we think in terms of a unit which we are comparing for having a hot beverage like tea or coffee, how do these compare? So, there is this paper, the two papers by Hawking. The first paper is a comparison of the paper cup with a polystyrene foam cup, and there is another, so there is a paper versus polystyrene cup, and you can look at we can also, so for each of these, for a given amount of liquid to be the given capacity of the cup. So, in this case this is an 8 ounce cup, and the entire life cycle analysis has been done. In the case of paper, it starts with the wood, which is the wood and waste, and in the case of polystyrene, it is using it starts from petroleum as a feedstock. In each of this, the paper making process is energy intensive, also requires water and other resources, has environmental impacts. So, based on a certain amount of cup, certain quantity, the entire chain has been drawn up, and based on that, the amount of energy and materials which are embodied or required in this is calculated. So, just to give you an idea now, if we look at ceramic, plastic, glass, paper and foam, we can, the weight of the material per cup is given here, and you can see the difference in this. The polystyrene cup is about 1/4 this mass of the paper cup. However, the specific energy per kg is much higher for the polystyrene cup, and but still the total embodied energy is lower than that of the paper cup. So the Hawking in his first paper makes an argument that one thinks that the paper cup is likely to be environmentally better, but he says that the polystyrene cup turns out to be better than the paper cup. Of course, this is dependent on the kind of assumptions and the so this is, and this comes out to be, so you get 0.2. If you look at this, the functional unit is 1 cup, and each of these cups are of the same capacity, and you can see this is 0.20, this is 0.55. When we look at reusable cups, ceramic, plastic and glass, you can see the difference in the, you can look at the original paper so that you can see more of the details. I am just giving you the final results, which will give you an idea of how this can be used. So you look at the cup mass, the material specific energy, and then based on this, when you multiply this, this gives you the embodied energy or the energy per cup. Now in the case of reusable cups, what would happen is that the number of reuses, as well as we want to make sure that this is done hygienically. So this will mean that we will need energy to wash, and the calculation which has been done by Hawking is for using the cups in a dishwasher, and the energy used in per wash is computed, and that is added, and based on this we get a situation like this. Depending on the number of uses, you can see that there is a trade-off between the foam cup and the paper cup and the reusable. So if you look at the glass, beyond a certain number, which comes out here, this is the break-even number of, if we are going to use it for, let's say, 40 or 50 times, then you can see that it is going to have a smaller energy per use will be much lower. However, if you are using less than 10, you can see that this is lower than this. So the paper cup turns out to be, and for the foam cup, you can see that it actually seems to be quite, the energy use is lower than the requirement for the reusable, until you go to a very large number. So this is an interesting, of course, if we change the assumptions and the way in which we process, the results may change. And so if you look at this paper by Hawking in Science, there was a critique and then there was a discussion. So the assumptions, depending on the assumptions one makes about the process, the things can change. Also, both in terms of polystyrene and paper, the process, and glass and ceramics, actually, there have been process efficiency improvements. So these are relatively old, these are in the 1990s. If you did the numbers today, you would get slightly different numbers, a little more efficient as compared to the earlier. So I would suggest that you look at both these papers, and this will give you an idea of one of the earliest ways in which one has done the life cycle analysis and an energy and environmental impact analysis for something that we always look at, the different kinds of choices of disposable versus reusable. Now when we think in terms of different energy sources, if you look at, let's say, extracting coal or extracting oil, in a period of time, what happens is that if we look at an oil well, we have an oil well, we need to input in different kinds of materials will come into the extraction process. There is a certain amount of energy which is used, that is the auxiliary E self. There is a gross energy input which is coming from the oil, and then there is a net energy output. This is going to your economy. So, we would like to see now here, if we look at it, there will be some materials and then there will be energy which is purchased. So, typically it might be using electricity, and we want to look at this boundary to see all that we are using, all that we are putting in is E self plus E purchase. And the energy return on investment is defined EROI as E net E self plus E purchase. Now, there are many different energy sources. We do not take the content of the oil or the coal which is there in the ground, whatever we are using in the process, and this can be done at the primary or it can be done up to the final use. In the final use, if we are looking at it up to the final use, it means whatever energy is being used in all the processing, finally when we are supplying that energy and over the lifetime of this process, what is the energy return on investment. So, this is called energy return on investment. Just like we did the the return on investment for the financial terms, this means that how much energy am I investing and how much energy am I getting out of it. So, typically what happens is in the case of in the early years when we had the oil well, this energy return of investment was high. This has now been coming down, and if you look at this, we can see there is a paper by Cleveland in the Journal of in the Energy Journal in 2005, and it shows the energy return of investment starting from the early 1900s and then going down, and so you see the energy return on investment for oil has gone down, for coal and so on. So, this is of the order of 100 and it has come down to recent. If you look at a coal based power plant, there would be the energy inputs are all provided in the initial year. When it starts operating, there is a whole set of embodied energy because you have the steels, you have all the materials which are coming in to construct the power plant, and then so this is all the energy which is invested. During the operation there is an auxiliary use which is the self use, and then there are materials and other embodied energy which is the O&M. So, the net which we are generating is this, and when you subtract this will be the net output. We can see how many years it takes to pay back for the energy which is invested in the life of the power plant. And in all of these, when we do the levels of analysis, we can look at different sets of levels. So, at the first level is we can just see in making the power plant what is the amount of embodied energy. That means we see how much of steel, concrete, the steam generators, piping systems, the assembly energy. So, this is the this is one level of calculation. Then we can go to the aspect where we look at what is the amount of the how much energy is going into the production of the steel, and then the iron ore which is coming into making that steel. So we can go to that level, and we can also then look at what is the energy which is taken in making the equipment which makes all of this. So one can go to different levels. Now when you go to the next level, you have to stop somewhere. So you have to see, if I go to the next level, how much additional amount, what percentage does it add to my overall numbers. So at some point we may make that closure and then go ahead. So one of the calculations is, in all of this we calculate not just the energy, but we also look at what are the amount of emissions which is coming in. So local and global. Just to show you an idea of the CO2 emissions of coal-based power, you can see that it starts with the mining, the transportation, the construction and power plant operation, and this is the study done by Mann and Spath and NREL, and this showed that most of it, the largest chunk of it is in the actual operation of the plants. Some of it, 3% is for mining, 2% transport and so on. But predominantly it comes to about a kg of CO2 equivalent per kilowatt hour. Similar comparison has been done for biomass, and the net energies, biomass is considered to be almost carbon dioxide neutral, because what happens is that the biomass during its entire growth cycle actually acts as a carbon sink. So the CO2 which is recycled in this case is of the order of 890 grams per kilowatt hour, and the net CO2 emissions, again depending on how we do the numbers, is just 46 gram per kilowatt hour as compared to that 1 kg per kilowatt hour. And there's feedstock production, the transport, the construction, and the CO2 emissions here which gets absorbed at that. And so overall there's a 98% CO2 closure. In IPCC considers biomass, if it is done sustainably, to be a carbon neutral option. So it's actually taken as zero CO2.